Welcome back to another Super Magnet Man video. This time we will be talking about radial ring magnets. About 20 years ago, we first started getting requests for radial ring magnets, especially out of neodymium. Well, at that time, we couldn't find any that existed. So we came up with the idea of making our radial arc segments. And I talked with the factory and we got them to make these with arc segments. And they've been making them for us for the last 20 years. We've got a couple of different sizes. These work really well when you just need a super strong field, and we can get these made in any different size. The advantage that we found from this is we can make them in many different sizes, really large, but we are limited as to how small we can make them. All right, now we have the true radial. Several years ago, they finally perfected the ability to make a single piece radial ring magnet. All one piece, magnetized from inside to outside. And on the inside you have one pole, and on the outside you have the other. So we could have north here and south here. That gives us a true radial ring. Another technique people developed several years after the arc segments came out was, why don't we just push two axially magnetized magnets together with the poles repelling and create a radial ring this way and epoxy it together. And that works, but they're a little bit hard to make. So what we want to do is take a look at the difference between these magnetically. What really makes these different? And so we'll start with the arc segments and the true radials. They are true radials because the inside circumference has a south pole or a north pole, and you have the opposite pole on the outer circumference. So if you look at the flat faces, you get this profile. This is the magnetic profile. You see the flux come out here and loop around. That is a true radial. Now, when we push the two ring magnets together, it's a little bit different. And that's why I wanted us to take a look at this. If you do this, remember your faces of the ring is north versus north. So when you push those together, you force the field out in between them. Now what you get is a north on the inside and north on the outside, and you're getting the opposite pole on the flat surfaces. So this gives us something different to look at. And one of the things we're going to do now is take a look at what that flux pattern looks like, and we'll show you our setup and how we got that information. To take a look at the field profile or the flux profile on these magnets, we wanted to create our own setup where we could get the information as we go around it. So we have a laser cut table that allows me to rotate around the magnet in 10-degree steps. And that's some of the readings you'll see in just a minute. We're using our Gauss meter that's given us an XYZ Gauss meter. It's a 3-axis probe, so we're able to find the exact spot where the magnet is the strongest going up and down, and then we back it up so that it is exactly touching the surface of the magnet. When we do that, it gives us the accurate data that you can tell. What we're looking at to begin with is our arc segment magnet. This is the one that's the arc segment. We did the same thing with the radial ring magnet and with the two rings forced together that are axial. And you'll now see the data as to what it looks like with each of these different flux plots of the outside circumference of these magnets. As we start, we're going to take a look at first the true radial ring magnet. This is a neodymium true radial, and first I want to orient you to what this graph is. This is a radar chart, and it goes around 0 to 350 degrees, and this is the plot that we did with using that table. And you'll notice that all the way out at the edge, this is our maximum reading that we were getting with the true radial ring magnet against the surface. Then we go into the green line, and the green line is 3 millimeters away from the surface. Every reading was taken 3 millimeters away. And then the red circle that's down in the middle was with it 6 millimeters away from the surface. So this gives us an idea. Looking at it with actual instruments gives us a very smooth plot. Now we'll take a look at what the modeling software tells us. We did the full model of this as a radial ring magnet, and This one gives us just exactly what we would expect, a nice smooth field all the way around it. And if you look down at the bottom, this is like a cross-section cutaway. We did a second model so we could see what the field looks like at this point. And you can see the flux travels through. You're going to have one pole on the inside circumference. You have a different pole, the other pole, on the outside circumference. So the flux travels around from one circumference to the other. This is a true radial. Now we're going to take a look at the arc segments. The arc segments are the common ones that we see, and you'll notice these dips on the readings. That's where the magnets meet, and they're touching each other, so there's a little bit of a gap here, and it gives us these little dips. The blue one, again, is on the surface. The green one is 3 millimeters away, and the red one is 6 millimeters away. So let's see what the modeling software tells us with this one. As we look at this, you also see the same dips, 12 dips, because there's 12 magnets that are joining together. You can also notice when you look at the cross-sectional area down below, you'll see that the flux is coming out and going around, and it is giving us a true radial profile exactly like we would expect. One pole on the inner circumference, the opposite pole on the outer circumference. Now we're going to look at those repelling axial ring magnets. And when we look at this one, first I want to explain, it's still to the same scale, but you see this sort of flat side. This is just due to the creating of the ring. I think the air gap is a little bit more. The epoxy layer might be a little bit thicker here, and on one half of the ring, I remember when I made it, I had half of the ring in the vise, and I was pushing it together with a vise, and I just didn't have the other half in there, and it, as you can tell, it must have not flattened out completely, and so it leaves a little bit of a gap, and those readings were consistently just slightly lower at that point. And now we'll take a look at what it looks like from the modeling software. And here you'll see this intense red field on the inner circumference and red on the outer circumference. And from the modeling perspective, that was a north pole on both of these, and that's what we're talking about. You look at the cross-section and you'll see the inner circumference and the outer circumference are both the same field. And you can follow your little vector arrows, and it's coming out of the inner circumference and going in the side. You check it on the outer circumference, it's coming out and going in on the sidewall. So it's exactly like we would expect and what we saw from the magnet data itself. Now we know that everybody would like to see these all at the same time, so we put them on the video together, combined them. Now that we've explained the graphs a little bit, full size, it'll make a little more sense to see them. From left, you see we have the repelling, then in the middle we have the true radial, and on the right we have the arc segments, and you can see how each of these compares to each other. So, what does all this mean? Let's put together the pieces so that you can make the best decision for your application. First of all, we have the radial arc segments, and these are extremely good. You do see that imbalance on the field that's on the outside, but if you really need a large magnet, let's say you needed one 8, 10, 12 inches in diameter, you're stuck with the radial arc segments. That's the only magnet we can make a ring in that size. If you really need the higher strength, we have the full range of magnet materials that we can work with and put them in radial arc segments. When it comes to the individual single piece ring magnet, it's the most expensive. If you wanted 100 pieces of a magnet that was exactly the same size, comparing it to the ring magnets or the arc segments, this magnet would cost you 3.5 times as much per piece if you're only getting 100 pieces. If you jumped it up to 1,000 pieces, they're getting very close to the same price. 2,000 pieces, this would be a cheaper option. But that's what you're faced with, is the cost. This also has size limits. They can't make an outside diameter bigger than about 60 or 70 millimeters. They can't make a thickness over about 10 millimeters thick at this time. So there are some dimensional constraints we would have to talk with you about on this one. Then we get to the ring magnets that are axial and forced together. One of the advantages is you do have the same pole on the inside as the outside, as the inside circumference as the outside circumference. That's the same pole. And it gives us some interesting things we can do. We got a little mocked up sample to show you. This is one where I have, these are ceramic ring magnets, axially magnetized, that I have glued together, and I have got them in this wooden frame so that we can demonstrate that we create this push-pull effect. Since the inside of this is north and the outside of this magnet is north, they want to repel each other. But since the face of this magnet is south, it wants to be attracted. So it allows it to create this spring effect, and it just sort of stalls out in the middle and will stay there. Now, it's not holding and suspending in 3 dimensions. I have the holes and this shaft that are holding it in the 3rd dimension. But as magnetically, it is perfectly balanced and just stops at that point. So I wanted you to understand the different options that you have available to you when you want a radial magnetic field. So if you have a specific application using this, don't hesitate to ask us, because we'd love to help you solve that problem. Thanks again for watching.